This is a canonical example of analogy. We look to explain why, when we say man is to king as woman is to queen, it is often found that the word embeddings produced particularly from, say, Word2Vec satisfy this linear relationship where we can take that for king minus that for man, add the embedding for woman, and we approximately find that the embedding for queen. More specifically, if we look at these, if we plot them, we find that this linear combination here, we don't find queen there, but we find queen is the closest one. So in this talk, we look to explain why that's closest, and in doing so, explain this gap, and in effect, why that gap there, or here, highlighted here, is smallest for queen. And you can see, just by the by, that other semantically related words are nearby, and a random assortment here are sort of further away. But we're looking to explain this gap. So just to set the scene, these word embeddings, if we look at Word2Vec, the structure of the model is very simple. We just have two embedding matrices, W and C, and for a given target word here on the left, we look to predict the distribution of context words seen around that word in a corpus. So the original paper by Mikolov starts by considering this distribution over all context words given a target word by computing the softmax over this layer here. But for computational reasons, they changed that to use a sigmoid function with so-called negative sampling. And it was shown by Goldberg and Levy that this rejigs the maths, and the dot product of a target word embedding with a context word embedding gives this PMI, which is a simple term from, the simple log ratio of the joint distribution to the marginals. And it's offset by this so-called shift term, which just simply comes from the choice of how many negative samples you use. And overall, this gives this implicit matrix factorization of a so-called shifted PMI matrix by the two embedding matrices. So the actual word embedding in each case is this vector of coefficients linked to the relevant word. So the overall plan then is to explain why we can say this. So we link this phrase, this analogy phrase, we break that down and sort of redefine it mathematically as these word transformations from man to king and woman to queen. And we link that to paraphrases, and we show that paraphrases induce this, the linear relationship we're looking for, but between PMI vectors, which are, if you like, rows of the PMI matrix, very high dimensional, like n dimensions, where n is the number of distinct words in the corpus, so perhaps millions. And from that, we get the relationship we want to see between the word embeddings in maybe like 200 dimensions or 500 dimensions or something, so a massive reduction. So what we're looking to do is move from semantics through to high dimensional geometry through to then the low dimensional embeddings. So this is a plan. So we need to fill in this gap. First of all, though, we have this last stage already explained by the relationship from Goldberg-Levy. That is, by considering word embeddings as low-dimensional projections of the high-dimensional PMI vectors, then if we have this relationship, if we can show that we get this relationship in the high-dimensional PMI vectors, then we automatically then have this, the relationship is maintained in the low-dimensional word embeddings. So we now need to explain how to get from here to here. We start by considering paraphrases. Paraphrases is what we typically intuitively mean. A word paraphrases a small set of words if those two are sort of semantically interchangeable in the text. So, king paraphrases man and royal, if you like. And if they paraphrase, then the words we see around them should be similar, i.e. the distributions over all the words in the dictionary given here. This is just a little cartoon. This is obviously a discrete distribution, but we're just looking to sort of give the intuition that the distribution over all the words in the dictionary induced by the paraphrase word, say king, should be similar to that distribution induced by the small set of words, say man and royal. More formally, we can then define a word paraphrasing a word set with if the paraphrase error is small, where the paraphrase error is simply then the log ratio of these two distributions. So this is a vector, n-dimensional vector, a very large dimensional vector. So why do we want to do this? If we consider these PMI vectors of two words, and we look to paraphrase words 1 and 2 by a word W star, then we can consider how well this relationship holds. This is, as I said, this is an n-dimensional vector. If we just consider the error, the difference, if you like, component-wise, that's just something like this, or more explicitly, this. We can add in these terms for free. These are logs of the same thing, so these are just zeros. But these are terms relating to the joint occurrence of words 1 and 2. By doing this, we can rejig and rearrange it into this format, where now these terms can be semantically kind of interpreted. Here we see the paraphrase error that we just referred to, and these other two terms. So if word 1 and 2 are paraphrased by word star, then this term should be small, the paraphrase error. And we find these other two terms where we can notice that W star, the paraphrase error we might be looking for, doesn't appear at all. These are just inherent to the words 1 and 2 that we're trying to paraphrase, the interaction between those two words. This is a set of conditional independences, and this is sort of, if you like, mutual independence of those words that we're trying to paraphrase. So this is, if you like, regardless of the word you're trying to then consider as the paraphrase word. Formally then, we can see that the PMI vector of a paraphrase word is the sum of the PMI vectors of the words you're trying to paraphrase with these three error terms. The paraphrase error, which should be small if there really is a paraphrase, and then these inherent conditional dependence or dependence errors that just simply come from the word set you've chosen to try and paraphrase. This is just repeating that. But what we can now do is generalize this and replace W star, a single word, by another word set. So we're considering that one word set paraphrasing another word set. And it's simply the same sort of intuition. We say one word set paraphrases another word set if the distribution of words seen around those word sets when they appear together are similar. And we can then extend lemma 1 to lemma 2, and we simply replace this single PMI vector with this sum of PMI vectors over this one word set and equate these two sums of PMI vectors over each of the word sets subject then to these error terms and the extent to which those word sets actually paraphrase one another, and these inherent error terms which just come from the statistical interactions of the words within those word sets. And one thing to note is that now we go from having one of each term, which aren't the same sort of term. It's almost like if they cancelled, it would just be coincidence. Whereas here, they're now they're two error terms, offsetting error terms of the same type, and it's more intuitively possible for these to cancel if these word sets are suitably chosen. Again, just repeating that here. And turning it to the specific example we're considering, we can choose W as woman and king, we can choose W star as man and queen, and then we immediately have then this relationship. So we have this relationship between PMI vectors which we're looking for, and we have explicit then error terms subject to the interactions of woman and king and man and queen. And we absorb, assuming this paraphrase holds, we absorb the paraphrase error just here into the approximation. So we start now having the relationship, geometric relationship we're looking for. And that completes a step in this path. And now, importantly, we've linked from geometry through to semantics, but not the semantic relationship we're looking for. We're saying that this paraphrase is a sufficient condition for this relationship between word embeddings, but it's not the semantic relationship of an analogy. So we now look to explain how these two are the same. And in fact, it's just a change of perspective. We look to reinterpret a paraphrase as a word transformation. So what we now do is, if you like, arbitrarily, we can pick a word out of W and consider the word set W, and consider this, this type of paraphrase, say man and royal by king, as actually just a word transformation from man to king by adding royal. Nothing's changed in the maths at all. This is simply just a way of viewing this. And we can extend this, we can consider the added word here as contextualizing the other word. So by contextualizing man, by adding royal, we make the induced distribution more similar to that of king, and therefore we kind of induce the paraphrase. Extending this then to word sets, the paraphrase of one word set by another word set can be thought of a word transformation from a word in one of those sets to a word in the other set, here W and W star, by adding the other words appropriately to each of the words, such that there's a paraphrase here. And so we can see this, we can just reinterpret this paraphrase here as a relationship, if you like, between these two individual words. And we can go further and look at that, if we more intuitively, if we want to consider this a relationship from small w to small w star, it makes just intuitive sense to just rejig this in our minds as seeing this as adding these words to w and sort of subtracting these words, just analogous to algebra. So we end up with this word transformation from w to w star by adding some words and subtracting other words. And we can think of this, this is just a repeat, we can think of this as the added words as narrowing the context of W. And these words here as then broadening out the context. And in effect, if we go back to, if we consider this as man and king, whereas a simple paraphrase you can think of as adding words to man to get to king, so we might add royal or reign or crown, and they each may do a sort of a rough job, but now we have a richer dictionary to explain this difference. In particular, we can explain the difference between man and king as using the difference between other words. And specifically, then we can say that WA is to WA star as WB is to WB star if there are words that will simultaneously transform each of these pairs. And so this is a mathematical kind of redefinition of what it is to say this. So we just interpret this as there being two word transformations that use the same words. And the same words is crucial and kind of reflected in the as term. So, specifically, we say man is to king as woman is to queen if there are words that will transform man to king and at the same time transform woman to queen. That is, we can complete this picture. So we say this if we can say this, if we can complete this picture for some particular words that are common in both of these diagrams. And we can do this actually. We don't have to trawl the dictionary for this. We can do this by simply setting W plus here to king and W minus here to man. And we see here, this here becomes trivial. If we say man plus king is the same as, if you like, king plus man going this way. So i.e. this holds if man and king paraphrase king and man, where the ordering here is irrelevant. And so this holds trivially. And what we're saying, though, is that by saying this, those same words must also fulfill this transformation. So woman plus king should paraphrase queen plus man. So what we're doing then is we're interpreting this mathematically and saying that is true if there's a paraphrase here that holds between woman and king and man and queen. So, sorry, let's jump. So this then completes the step that was missing in this path. So we say man is to king as woman is to queen if these two word transformations hold. We can find words that satisfy those word transformations. And on the one hand, we have the trivial case. On the other hand, this paraphrase must hold. And these are just if and only if kind of reinterpretations of each other. And then we know that if this paraphrase holds, then we have this geometric relationship between PMI, high-dimensional PMI vectors, subject to known error terms. And then by projecting down to low dimensions, we have this relationship between word embeddings, and we have completed the link between semantic analogy relationships and the relationship observed between word embeddings. That is to say then that man is to king as woman is to queen. If we say that, then it directly implies that we have this relationship between word embeddings with known error terms. That is then, going back to the original picture, we can now explain this gap between this linear combination here and the word embedding for queen as specifically these three error terms that we've seen before, these dependent error terms, and then this paraphrase error term. And because those error terms are smallest for queen, because of all the steps in the argument, then queen is then necessarily the closest word embedding to the point here that we're looking for from the linear combination. And that concludes the proof. Thank you.
Does this type of analysis or these methods can be potentially used for other forms of analogies, say visual analogies, or you think this machinery is pretty specific to language?
I think it probably could be extended to other domains. I'm not sure specifically for vision, but one area in particular, Wörterwerk is used quite a lot in embeddings of graphs, and like specifically embedding each node in a graph. And there, I think I can imagine there would be analogical relationships between different nodes, like friends in a Facebook graph or places in a transport graph, that kind of thing. That's where I can see a specific kind of like most obvious, if you like, translation.
In the cases where the linear algebra fails to produce a sort of plausible English analogy, as you sort of try it, you plug it in, and you're like, this doesn't really make sense. Were you able to analyze the sort of three error terms here and get a better understanding of under which conditions you would expect these to be analogies and under which conditions it might fail?
Yeah, no, that's a good point. That's if you like ongoing work. So. Yeah, there are some cases where, I mean, in short, it's all down to these error terms and very specifically the relationship between the two words. So if the two words you're trying to paraphrase are quite, I mean, we can just think of intuitively related words. If you're trying to paraphrase two words that each cause each other to be more likely to be seen, maybe in certain contexts or maybe just in general, then that interaction is going to necessarily damage, if you like, the analogical relationship you're trying to find. Some of that I think will just bear out and fit intuition, but to sort of like analytically show that's sort of, if you like, work in progress. But I think you can kind of, just from initial stuff, you can kind of see this sort of tying in with what you'd expect, if you like.
Cool. Well, let's thank the speaker.
Thanks. I'll be at Poster 101, and there's a few follow-up works on archive if you're interested. Thanks.
My name is Stanisław Jastrzębski, and I will be presenting our work on parameter-efficient transfer learning for natural language processing. This was led by Neil Hosby and co-authored by me during my stay at Google AI. So imagine we are doing transfer learning for natural language processing. The necessary ingredients as of now include a large pre-trained model, and we'll focus on BERT, and a procedure to actually train weights, and we'll focus on fine-tuning, which is a state-of-the-art approach. So in this case, for each of the tasks, we will copy the weights, adapt them, and then store them. However, this can become prohibitively costly if you have a lot of tasks. This can happen in few situations. For instance, if we move towards a future where we have a single, very large and very capable model, we might wish to transfer it to many, many tasks. For this type of settings, we use another approach. We propose small adapter modules that have very few parameters, and we tune only them for each of the tasks, and we keep aside the large pre-trained model. More precisely, on the right-hand side, we have transformer module, or more precisely, a single block of it. It has two stages. It has the multi-headed attention and the fit-for layer. And in each of the stages, we'll insert our potentially tiny adapter modules, and we'll tune only them. The adapter modules work as follows. They take the hidden state, and they simply project it down using a bottleneck layer. And now, by scaling down or up the bottleneck size, we can reduce or increase the number of parameters that we use in our adapter module. We run experiments on a few settings. I will here talk through our glue benchmark results. The glue benchmark consists of 10 tasks, and we report the results as follows. We'll have on the x-axis our budget. That's the number of parameters that we use for each of the tasks. It will be on a log scale. On the y-axis, we have accuracy delta. So that's how many points in accuracy we have lost compared to the naive and very parameter-hungry method that is full fine-tuning. Now, we'll compare between two approaches. The brown line is our solution. As I said, we achieve more lower budgets by simply reducing the size of the bottleneck down to even a few neurons. Now we'll compare to the blue line, which is the naive fine-tuning, where we achieve lower budgets by simply tuning only a few top layers, and at the end of the spectrum, just tuning the final classifier. Now, comparing between the two, we see that our approach for a range of parameters achieves a similar stable performance, while the baseline, while can achieve more parameter-efficient solutions, does that at a high cost. To highlight, looking at the left spectrum of the plot, we see that we can achieve 96.4% reduction in the number of parameters per task, while incurring only 0.4 accuracy drop. So, to conclude, if we move towards a single model future, or we have, for instance, a cloud application where we want to have a model for each of the clients, it seems like we need to improve parameter efficiency of transfer learning. To this end, and specifically for natural language processing, we propose a module called Adapter, where we drastically reduce the number of parameters needed for each task, for instance, achieving 30x reduction in the parameter cost for only 0.4 accuracy drop in performance. I wanted also to point out related work by Stickland and Murray from the University of Edinburgh that analyzes a very similar setting and proposes a related approach. And finally, please come to our poster today at 6:30. Thank you very much for your attention.
Morning, everyone. Excited to be here. I'm Sujit Ravi from Google Research. I lead a few different ML teams. So a lot of our group's work is focused on large-scale machine learning, deep neural networks, graph structure neural network for semi-supervised learning, a lot of applications in NLP, conversational AI, and also computer vision. As a different area of focus we have for actually designing more efficient neural networks specifically for on-device applications. So the main motivation for us is we've been very good at designing these huge networks that give you great accuracies that are running on the cloud. How do you translate some of that success to tiny neural networks? In other words, compute and memory constrained neural networks that are running on devices like your smartphone and smartwatches. In general, I mean, the question is, can you design networks more efficiently rather than just like thinking about it ad hoc, for every new task? The reason for doing on-device for us is privacy is a big one of the core concerns because you don't want the data to go from the device to the cloud for many applications. So this is an important reason why we do it. Connectivity is another one. Just because your Wi-Fi stops working, if your application stops predicting, giving you suggestions either in text or image space, that's actually a bad experience. Efficiency, I already pointed out. And finally, consistent experience. So like if you're talking to like voice assistants, you need a consistent experience. And so you need some of these computations to happen on device to ensure that it's actually seamless. This is not aspirational. You can already see many of these things working, in particular like the work I'm talking about, like some of this is already powering image recognition on your phone, and also applications like Smart Reply. You can automatically respond to chat messages, and you can plug this into any app on your smartwatch. Here are some links if you're interested. Obviously, so there's a lot of challenges, like, if you have to make this work, I'm not going to enumerate them, but you can think of some of the obvious ones, like hardware constraints. But one of the core things is we want to design these networks efficiently, but also do it at near state-of-the-art performance. This is actually the challenging part, right? So there's a lot of work, but many of them degrade with task complexity. In general, we are trying to build like small and fast models, but also at generalizable and near state-of-the-art quality. You can do this, and so the work we propose is like, doing efficient generalizable deep networks using neural projections. And the key idea is like we train these models, but they're very fast and small. You can combine them with other hardware acceleration, et cetera, to get even better performance. But the optimization itself follows a joint strategy, but you can also train these in isolation. In the interest of time, I'm not going to go into this. But the core idea is that we design like these sort of projection layers inside the network, which basically transform intermediate features and representations inside the neural network into compact bit vectors. And the idea is like we can do this dynamically in a very memory efficient fashion. So you transform like these high dimensional or even dense vectors that are semantically similar into compact vectors that are sort of nearby in having distance space. So they're very nice like generalizable properties for this, some details in the paper. But even better, this generalizes to different types of networks. So you can actually design convolution networks with this, recurrent networks with this. There's a series of works from our lab and collaborators on this, like projection CNN was in this paper, but last year we introduced what we call self-governing neural networks, which gives you sort of state-of-the-art performance for some of the NLP tasks at like almost 100x compression rates. You can also transfer them, basically think of embedding matrices, replace that with these parameterized functions, and you can transfer it to new tasks. Also, there are a series of works on how do you improve them in a, make it more structured. Lots of results in the paper, but just to give you an idea, on one of the intent dialogue understanding tasks, you can get near state-of-the-art performance with a network that's just like few hundreds of kilobytes in size. And this is actually a deep network. So I think very exciting times. If you want to do this for yourself, like you want to train your own models, we announced something called Learn to Compress last year. We'll probably have more things coming out. Stay tuned. Finally, here's a link to the paper. And just as a plug, we have a workshop that's happening on Friday on this topic on device machine learning with like some wonderful colleagues from both academia and industry. If you're interested, please come and check it out. Thank you.
Hello, everyone. My name is Nikos Papas, and I'm going to present our joint work with James Henderson on output similarity structure learning for neural language generation. The main problem in neural language generation is essentially predicting the next word given the previous ones. A typical way to approximate the conditional probability distribution at time t given the context vector ht is with a linear unit with weights w and a bias b. One limitation with this familiar output layer parameterization is that it depends on the vocabulary size v, which makes it sample inefficient, especially when we deal with very large vocabulary spaces with a long tail distribution. The second limitation is that the output layer power depends on the hidden dimensionality or rank D of the log probability matrix D, which is also known as the softmax bottleneck. And typically increasing the output layer power leads to high overhead, and the model is prone to overfitting. Output similarity structure learning methods, which have been used for few-shot and zero-shot text classification, have the potential to address both limitations. However, currently they address only the first one, given that their parameterization no longer depends on the vocabulary size V, which makes them more sample efficient, and they have also the ability to transfer across output labels. However, the second limitation is still holds, and this is what we address in our paper. So previous such methods have a similar output layer form as the previous one, with a main key difference that the output labels are encoded in the same way that the context is encoded, given the same word embedding E. This allows them to represent arbitrary output labels, given their textual descriptions, and essentially transfer across output labels effectively, something that the previous parameterization is not able to do because it doesn't have parameter sharing. So previous label encoder networks, such as weight tying, bilinear mapping, and dual nonlinear mapping, have cellular architectures and are not able to capture as rich relationships across outputs. Our contributions in this line of work is that we provided generalization over previous output similarity structure learning methods for this task, which preserves their sample efficiency. And we also propose a deep output label encoder network, which has dropout between layers to avoid overfitting. And we also increase the output layer power with representation depth instead of increasing the rank or dimensionality D, which leads to a low overhead compared to the original parameterization. Our label encoder network has the following properties. It shares parameters across output labels with k subsequent nonlinear projections. It preserves information across layers with residual connections to the input word embedding and also to the outputs of the previous output layers. And it also avoids overfitting with standard or variational dropout for each layer I equal 1 to k. The standard dropout essentially samples a different dropout mask delta for each output label, and the variational one samples a single dropout mask and applies it to all output labels. Our evaluation on two text generation tasks show that our output layer is able to improve competitive, recurrent, and self-attention architectures without increasing their dimensionality or rank. And by having a low overhead compared to them, note that our approach reaches similar performance with other methods with higher computational overheads, which increase the dimensionality or rank. Finally, we find that we are able to better transfer across low resource outputs, as we can see on the right-hand side, by plotting the cross-entropy difference between our method and the previous ones over different word frequency bins. If you want to know more, please come to our poster at 1:04 this evening. Thank you for your attention.
My name is Dylan. Today I will be talking our work combining advanced training to improve language modeling. This is joint work with Chen Yuegong and Chang Liu from UT Austin. So the goal of language modeling is to predict what word comes next given the context. The context is first modeled with a recurrent neural network, and then we train a softmax function to do prediction. And given a data set, the model parameters theta and w often join the train with by maximize the log likelihood. However, one main challenge in training language models is their tendency to overfit. For a quick example, here we train a strong baseline AWD-STM on the Wiki2 dataset. As we can see from the figure, that the training and the validation performance gap is kind of huge. Lots of techniques have been investigated in preventing overfitting. However, it still remains an open problem for training better language models. So in our work, we propose to augment adversarial training to improve language modeling. The idea is super simple. So we inject adversarial noise to the word embeddings in the softmax layer, and then seek to find the optimal model parameters theta and w that maximize the worst case performance. A key property of this formulation is that the optimal adversarial perturbation has a closed form solution. And the optimal solution is proportional to the negative direction of the context. And this allows us to derive an efficient algorithm and without introducing additional computation cost. So an interesting property of our method is that our adversarial training strategy actually promotes diversity in word embeddings. To see that given context H, if the probability of generate word WI is higher than any other words, in this way we can, by the definition of the adversarial training, we have that the inner product value between WI and H subject to the adversarial perturbation should be larger than any other word context pairs. That being said, for the minimum distance between WI to its neighbors should be larger than epsilon. It has been widely observed that promoting diversity in word embeddings could lead to better generalization performance in language modeling, and our method could be seen as a way to promote diversity implicitly, but with theoretical guarantees. We applied our method to improve language modeling. From the tables, we can see that our method achieved better performance than strong baselines. We also apply our method to improve machine translation with our adversarial training. Our method achieves the best performance in general. To summarize, In this work, we propose to improve language modeling with adversarial training, and the algorithm is simple and is super easy to implement in practice. And we show that our algorithm promotes diversity in word embeddings and demonstrates the strong empirical performance on several benchmarks. For more details, please check out our poster at 1:05 tonight. Thanks very much for your time.
Hello, I'm Tian Xiao. I'm very happy to talk about our paper, Mixture Models for Diverse Machine Translation, Tricks of the Trade. This is joint work with Maya Ott, Michael Olli, and Marco Aurelio Renzato. Translation is a challenging task not only because of its large and structured output space, but also because it is inherently a one-to-many mapping. A source sentence can have many plausible translations due to paraphrases or different translation styles. For example, danke in German can be translated into thank you, thanks, or thank you very much. Moreover, the information asymmetry between different languages can lead to different translation options. Sie in German is a general pronoun and can be translated into you, they, or it, depending on the context. This raises the question of how to model such multimodal output distribution, and how can we efficiently decode a diverse set of hypotheses such that users can express their preference for how to translate a piece of content. Specifically, the task of machine translation is that given a source sentence X consisting of words X1 to XL, we want to output its target translation Y from Y1 to YT. A standard neural machine translation model factorizes PY given X autoregressively into the product of the probability of each word given source sentence X and all previous words. Although this autoregressive factorization in principle can model any joint distribution, it also brings in challenges at inference time to search for the most likely sequences of Y. A commonly used decoding algorithm is beam search, which decodes a sequence left to right and maintains the k-best hypothesis at each step. Here's an example translation from Chinese to English. We can see that the hypotheses produced by beam search typically have very low diversity with only minor differences in the suffix. Yet human references are quite diverse, from it was rejected by 58% of its members who voted in the ballot to, of the members who voted, 58% opposed the contract transaction. So although beam search is often effective in finding one likely sequence of Y, it cannot explore these multiple modes. Instead of leaving all the uncertainty of PY given X to the decoder distribution and face this challenging search problem at test time, we propose to explicitly model uncertainty during training. The idea is to introduce a latent variable, Z, to capture different translation modes, so that we can better explore the search space through the latent variable and decode different Y from different Z. A popular latent variable model is a variational autoencoder that employs a Gaussian Z. Here we are modeling conditional distribution PY given X, and it decomposes into PZ given X times PY given ZX integrated over Z. Since this integration is intractable, a VAE is trained via a variational lower bound to the log likelihood. A big deficiency of VAE on text is that it suffers from the posterior collapse problem, where the posterior is always equal to the prior to avoid the KL penalty. As a result, the latent variable is ignored and cannot be used to facilitate search. We take a step back to consider a multinomial Z, taking values from 1 to k. So we have a mixture model with k components. It's the simplest latent variable model. We can explicitly enumerate Z and compute the exact marginal. We make it even simpler by setting PZ given X to a uniform distribution. So we assume each component is equally likely a priori. Furthermore, we assume the likelihood PY given ZX is only large for one Z, but nearly zero for others. So a particular translation Y is only explained by a particular component Z. Then we can approximate the summation by the maximum term. Taking the negative logarithm, we get our loss function. Training proceeds via the online EM algorithm. For each mini-batch, we take a hard E step to estimate the responsibility of each component for the training examples. So the component that best explains a training example takes the full responsibility. Then we take an M step to update the parameters through each component with log gradients weighted by their responsibility. It's just like training mixture of Gaussians, but in the text space and condition on source. To implement a mixture model, we make a slight modification to the standard model architecture by injecting the latent variable embedding at the beginning of the target sequence so that it is conditioned on Z. At test time, we generate K hypothesis by greedily decoding Py given Zx for Z from 1 to K. So it's computationally efficient and fully parallelizable. In this way, we solely depend on the latent variable to produce different hypotheses, so there's no need of heuristic diverse decoding methods. So far, everything seems nice and fine, so let's try out our mixture model with K equals 3 components. Unfortunately, all the components produce exactly the same hypothesis. The Z is ignored, and our mixture model degenerates to a baseline model without any benefit from the latent variable. Is this because that we are sharing too many parameters that Py given Zx doesn't have enough capacity to differentiate for different Z? So let's try using independently parameterized decoders for different components. This time, different components do provide different hypotheses, but only one of them is the desired translation, while the other two produces a single period. So here, only one component gets trained, and Py given Zx is poor except for one Z. This is because of the well-known rich gets richer phenomenon, where once a component is better than others, it receives more gradients, and others starve and eventually die. It turns out that mixture models are prone to two major types of degeneracies. Degeneracy type 1, all the components behave the same, and the latent variable is ignored. Degeneracy type 2, only one component gets trained, and others are poor, cannot be used to translate any source sentence. Now, how to train mixture models is not obvious. Let's take a closer look. Back to our shared parameterization case where the latent variable is ignored, let's examine our training procedure. At the E step, when we assign the training examples to the components that best explain them, a dropout noise here can confuse latent variable assignment and make the selection process random. We did an experiment to test the effect of dropout and see that as we increase the dropout probability, the optimal value of Z is quickly corrupted. Even with a small dropout probability of 0.1, we observe a 42% chance that the optimal assignment of Z changes, which in turn makes the model ignore the latent variable. The key to the specialization of different components is to make consistent use of them. So we propose to turn off dropout at the E step when we are assigning the responsibilities, and only dropout at the M step for gradients regularization. With our modified dropout strategy, all the components can produce high-quality hypotheses, and they are quite diverse from each other. From 58% of the members who voted oppose the contract deal to, of the members who voted, 58% oppose the deal, or 58% of the voting members oppose the contract deal. Finally, it works. So far, we've found out a success case, namely the hard mixture model with uniform prior, using online training schedule, shared parameterization, and turning off dropout at each step. We've also seen that if we use independent parameterization, then we encounter a degeneracy type where only one component gets trained. This could be caused by our online training schedule that interleaves E step and M step for each mini batch. So the components evolve too fast and with a prominent rich gets richer effect. This can possibly be remedied if we do offline training schedule, so we perform E step for all training examples before the M step, so each component receives enough training examples and it's more stable. Moreover, we just introduced a particular variant of mixture model, the hard mixture with uniform prior. We can also include a learned prior, or going back from the maximum to the forced summation to get a soft mixture. The different combinations of these design choices can lead to different model performance. Let's now systematically evaluate them and see what insights we can get for how to successfully train mixture models. We developed an evaluation protocol based on the BLUE score that measures sentence similarity using word n-gram matching statistics. It ranges from 0 when sentences have no overlap to 100 when they're the same. We compute the average BLUE of each hypothesis against the references to measure their overall quality. In addition, we compute the pairwise BLUE among the hypotheses to measure their diversity. We also compute human BLUE and pairwise BLUE for reference. We test mixture models and baselines on 3 benchmark datasets that uniquely provide multiple hypotheses at test time. Note that we only have one hypothesis at, they uniquely provide multiple references at test time. Note that we only have one reference at training time. We first experiment on the WMT English to German dataset with k equals 3 components. We plot pairwise BLUE in descending order versus BLUE. So the right side indicates high diversity, and the upper side indicates high quality. The star marker represents human performance, which has high BLUE and meanwhile quite diverse. The hard mixture model we introduced earlier achieves very good performance close to human. The variational NMT model, however, has pairwise BLUE 100, indicating its latent variable is totally ignored. Also suffering from this type of degeneracy are the softer mixture models with offline training schedule and shared parameterization. So slow evolution were combined with a little capacity to differentiate is not a good choice, especially when your training objective is the soft mixture, which doesn't explicitly encourage diversity. In contrast, if we do online training with independent parameters, then all the models suffer from another type of degeneracy where only one component gets trained and have a poor BLUE score. There are 2 settings that work consistently well: the online training schedule with shared parameters or offline training schedule with independent parameters. Different model variants provide different trade-off between quality and diversity. In particular, the online shared setting has higher quality than offline independent. This is as expected, as the independent components have less data to train each of them. Second, the hard mixture models yield more diverse translations than soft mixtures. It's just like how k-means tend to find clusters that are farther apart from each other compared to soft mixture of Gaussians. Overall, we recommend a winning model, the hard mixture, as it requires only one backward pass and is super fast to train, with uniform prior, so there's no prior predictor and it's extremely easy to implement. Using shared parameterization, so there's negligible amount of extra parameters, and online training schedule, so we don't need to restore the responsibilities for all training examples, and it's memory efficient. We next extend our evaluation to 3 datasets comparing our mixture model with decoding-based approaches, including sampling, beam search, and diversity-encouraged beam search. For all values of k, our model achieves the best trade-off between quality and diversity. We also find that our latent variable model can capture consistent training styles across different examples, such as tense when translating from Chinese to English. So Chinese doesn't have tense unless a time phrase is explicitly stated. So the first component tends to translate with past tense, whereas the third component tends to translate with present tense. Indeed, when we look at the generations, we find that for words like was, were, or had, their frequency from z equals 1 is more than 3 times higher than from z equals 3. Conversely, for words like has and says, their frequency from z equals 3 is more than twice higher than from z equals 1. Similarly, different latent values exhibit different preferences of using this versus that, percent versus the verb versus the symbol percent. To summarize, the output distribution py given x in conditional text generation is multimodal, and search for the most likely sequences of y is difficult. We propose to explicitly model uncertainty with latent variables to better search the space and decode different y from different z. Mixture models are the simplest and most well understood latent variable models in the machine learning literature. They work pretty well, but have hardly been explored for text generation. Training them is not obvious, and suboptimal design choices can lead to degeneracies. Through our extensive study, we provide recipes for how to get them work. In particular, we should turn off dropout at each step, and the hard mixture model with uniform prior, shared parameterization, online training schedule is the simplest one and it's most efficient. Our model is a strong baseline for work on latent variable text modeling, and it can be applied to other text generation tasks such as dialogue, image captioning, and summarization. It can even apply beyond text generation. So we have an ongoing project applying this model in chemistry to predict what are the possible reactants to get a target molecule. Then the model provides a diverse set of hypotheses so that chemists can later test them out. Our code is available online at github.com/pytorch/fileseek. If you want to know more, please come to our poster number 106 tonight. Thank you, and questions are welcome.
So if I was right, I remember that WMT dataset only have one reference. So how to get 10 references or 3 references?
So we collected for a subset of test set to hire multiple human translators to get more translation.
Okay, so did you check whether the 10 references are really diverse, or do you have some
Yes, we
methods?
have that star marker represents human performance, and it's quite diverse.
So one other way to get diversity is just do training 3 separate times with completely different initializations.
Oh, so that will degenerate. So that's like a special case of our mixture model that all components, they will, even from different initializations, they will finally converge to the same, like very similar solution.
Cool, thank you.
Oh, if there are no more questions, let's thank the speaker again.
I will present our work, a new pre-training method for language generation. This is joint work with Kai Tao, Xu Jianfeng, and Tian. So first of all, you may ask, given that BERT and GPT are very successful, so why do we need new pre-training methods? Of course, because we are researchers, so always want something new. Okay, that's just kidding. Okay. Actually, although BERT and GPT are very successful, but they are only suboptimal for some sequence generation, sequence-to-sequence generation tasks. As you may know, for sequence-to-sequence generation tasks, usually we need to base on the encoder-to-decoder framework and also with the attention module. Especially the encoder-to-decoder attention is very important for this kind of applications. However, BERT only pre-trains an encoder, or GPT only pre-trains a decoder, so they cannot well handle this kind of sequence-to-sequence generation tasks. So in this work, we propose a new method. We call it masquerade sequence-to-sequence pre-training method. It jointly pre-trains an encoder, a decoder, and the attention module between the encoder and the decoder. As shown in this figure, you can see that given a sentence, we mask a segment of k consecutive tokens, and then we use the encoder to encode this masked sequence and pass through the attention module and then the decoder. In the decoder, we want to predict, we want to recover the masked segments. Note that in the decoder set, X1, X2, and X7 and X8 are not invisible to the decoder, so that to recover the masked segment, the decoder must to attend to the encoder, so that we force the model to pre-train the attention module. And also because we need to recover consecutive segments, so the decoder or the model has the ability of language modeling. Actually, our model have some close relationship with BERT and GPT. So as shown in the previous slides, we have a hyperparameter k, the number of masked tokens. So if we set k to 1, then mask will degenerate to a specific case of BERT, the masking language model. But if we set k to m, to the total length of the input sentence, that means we mask all the input tokens. Then we need to generate, the decoder need to generate the whole sentence, one token by one token from left to right. So it will generate, this is exactly the case of GPT. And that means if we set k to m, we get GPT. So we test our model on different tasks. Here is the unsupervised neural machine translation. We pre-train the model on monolingual data and then do a neural machine translation. So you can say we compare with XLM. It's a recent technical based on BERT. So you can say we can achieve very good improvement over XLM on different language pairs and different translation directions. Here are the results on low-resource neural machine translation. We also pre-train the model on monolingual data and then fine-tune the model on downstream tasks. For example, if we have 10,000 or 100,000 and 1 million bilingual sentence pairs, you can see that especially when we have only few bilingual pairs, so we can get a very good improvement. We also test our results on test summarization. You can see that we also are much better than the baseline method. The baseline is based on transfer model. Okay. So we also conducted a study on the hyperparameter k. You remember that k is the number of tokens, so we mask it in our model. So you can see for different tasks, the previous two figures, the smaller the better. The last two figures, larger the better. So you can see, roughly speaking, if we mask half of the sequence, we achieve very good balance between the encoder and the decoder, and we get a better performance. Remember that k equals 1 is similar to BERT, and k equals m is very similar to GPT. So that means BERT and GPT are not very good for language generation, especially sequence generation tasks. Okay. So that's all. Okay. So our post number is 107. Welcome to our post for more details, and the code is available at the GitHub. Okay. Thank you.
My name is Limor Gulchin. I want to thank all my co-authors who couldn't be here today, and in particular to Adam Kalai, my supervisor for the project, who's really been the driving force behind this project. So thank you, Adam. The motivation for the project should be pretty straightforward. Who doesn't like killing a joke by explaining it? And these are the tools that we use to do that. We start with word embeddings, which I assume most of you would be familiar with if you're in this room. But in a few words, I'm just going to say that we're taking words that are, these discrete entities, and we're representing them as vectors in space, usually pretty high dimensional, about 300 dimensions. And we can say multiple things about their association to one another through linear algebra, basically. So through distance formulations and parallelograms and so forth. The data that we're using, first of all, you might be skeptical of what I mean by humor here. I'm talking about single word humor, and you might say, well, is that actually funny? Apparently it is. Comedians had this intuition for a while. Look at our paper if you want to hear more about that. But also psychologists have been studying this for a while, and we indeed started with one pre-existing data set with all sorts of single words and their associated humor ratings. However, that was an aggregate level data set, so we also set out to collect our own original data set from Amazon Mechanical Turk. And then we asked multiple users to both rate words as funny or not, but also we were interested in humor features. So we identified 6 humor features which map to all sorts of theories of humor that existed from previous literature in all sorts of fields, from Plato to Hobbes to Freud. They all had theories of what makes things funny, so we just set out to look for those. All right, so our approach was threefold, and we're asking the following questions. Can we use word embeddings to capture humor theories and a general humor direction in the word embedding, if you like? Also, can we identify different senses of humor across demographic groups? So this is going down the ladder of a generality here. And third, we are interested in whether we can define some individual sense of humor vector, which would be a mean vector of the words that a certain individual finds funny, and use that to predict the user's taste on newly unseen words. All right, so spoiler alert, the answer to all the questions is yes. That's why we're here. First of all, we can use word embeddings to capture humor theories and identify humor direction, basically by fitting a simple ridge regression, so a linear relationship. We can identify, as you see down there below, a humor direction in the data set that correlates with humor ratings. We also set out, as we said, to look for the 6 features in the word embeddings, and we can indeed predict them with a reasonable amount of success. And all the features that we identified were also positively correlated with humor ratings, as you see here. Come to the poster if you want to hear more about the details of the analysis. All right, secondly, if we just take that mean humor vector that I described, which represents an individual taste of humor, and we just cluster those, demographics actually emerged of themselves. So with these 5 clusters, I mean, the analysis looks pretty much the same no matter how many clusters we choose. The first cluster, as you can see, is quite predominantly female and prefers funny sounding words. You can see examples at the top part of the table. Cluster number 5 is younger and more male and prefers sexual humor, maybe not so surprisingly. And cluster number 3 was actually the most surprising to me. It's the older cluster that also seems to prefer insults and scatological humor. I'm not going to ask the older people in the audience to comment, but yes. And number 3, we did a know your audience test, we called it, and we took 2 individuals using these average vectors that we described, and we tried to match them to new words with a holdout set, and see if we can do this matching successfully. So as you can see, sorry, I have to stop here, but we did a reasonable job, and if you want to hear more or just see funny words in a table, please come to the poster 108. I'll be there. Thank you very much.
Hi, I'm Peter Liu from Google Brain. I'm going to talk about MeanSum, a model for unsupervised abstractive text summarization. This is joint work with Eric Chu from the MIT Media Lab, who interned in our team. There are 2 broad categories of summarization, extractive and abstractive. In this work, we focus on abstractive summarization because it's how humans do it, and we're interested in the goal of human-level performance. Abstractive summarization didn't really get much attention until the advent of neural language models, which enabled models to generate reasonably fluent text. Since then, most work in neural summarization has been in the supervised setting. The standard supervised approach is to train a sequence-to-sequence style model using large paired datasets of documents and summaries. This is fine if you have such data, but it's actually pretty rare, and most people use news-based data sets. If your data is not news, such models probably won't work so well for you out of the box, and you'll need to collect label data, which is very expensive in the case of summaries. Even for companies like Google, collecting large amounts of summaries is not scalable. And so progress in unsupervised approaches is very important. And in this work, we assume no access to summaries in training. We applied our model to review summarization without making specific modeling choices for this domain. In this setting, we have a bunch of reviews for a business or a product, and we want to summarize them. The high-level idea of our approach is we train a review autoencoder such that the mean encoding decodes to a reasonable summary in the form of a canonical review. Here's what the model architecture looks like. On the left is a standard autoencoder where each review is independently autoencoded and contributing to a reconstruction loss. The second component on the right imposes summarization-specific structure on the latent space. We take the mean encoding, decode a summary, re-encode it and then compute the cosine distance with the input reviews. This contributes to a summarization loss. The two losses are added together, and everything is trained end to end. One nice thing about this architecture is generation is part of training, and so there's no exposure bias from teacher forcing, which we found significantly improves quality. Decoding is not differentiable because of the discreteness of text, and so we used the straight-through Gumbel softmax estimator to approximate it. To tune and select models, we only use proxy metrics that don't rely on ground truth, which you can read about in the paper. For evaluation, we computed Rouge scores using a small ground truth test set, which we collected using Mechanical Turk. Even though Rouge is known to be biased towards extractive methods, we outperform a variety of extractive methods, including one near state-of-the-art. Now, Rouge doesn't tell the whole story, and we asked human raters to evaluate linguistic and summarization quality, and it looks good there too. In particular, the average fluency of the summaries is pretty close to human. Here's one example showing 8 reviews for a nail salon, and the model-generated summary, and the extractive model output. Colors here show corresponding concepts in the input and output, and you can see some pretty interesting paraphrasing by our model. For example, the phrases manny/petty and very relaxing don't occur in the reviews, but it's consistent with what they're saying. The language is also fluent and captures the overall sentiment well. To conclude, we showed how to do zero-shot abstractive summarization with neural models by moving away from sequence-to-sequence, conventional sequence-to-sequence approaches to a summarization-specific architecture. If you're interested in trying it, the code's available online, including model weights, as well as ground truth data. Finally, come to our poster number 109 if you're interested in learning more. Thank you.
So in this work, we'll show that incorporating knowledge from linguistic structure about a sentence helps to improve or make better prosody in text-to-speech. Right. In a nutshell, what we're doing is we are basically have a recurrent neural network in which layers are clocked at irregular time intervals. Okay. So let's look at the problem. Let's take a sentence. That's a super choice. I can choose to say that in a number of ways. That's a super choice, or that's a super choice, right? And what am I doing? I'm changing the pitch, the energy, and also the duration of the sounds. Right? And there's clearly very many different ways of doing it. So what we do is we use a conditional variational autoencoder to model this, right? So at the input, we give it the full sequence of pitch, power, and durations, and obviously same with the output. But in the middle, we have this bottleneck, which is a single vector that represents the whole sequence. Okay? And so where does the clockworkness come into this model? Right, so a sentence can be broken down into words, right, and each word has multiple syllables, and syllables typically can contain 1 to 4 phonemes, and then we get down to the frame level, which represents, say, 5 milliseconds of speech. All right? And so what we want to do is to add this sort of timing into the recurrent neural network. So we have layers that tick at the syllable rate, and another layer that ticks at the phoneme rate. And when we look at prosody theory, then it tells us that for things like pitch, we want to use syllable-sized units. But for power, we might want to use phoneme-sized units. And then duration, that's kind of a bit up in the air. Some people say phonemes, some people say syllables. We do it at the phoneme level. And so the topology is there, but then there's also the input features. which again tick at different rates. So there's structure in this network that allows us to incorporate phoneme level, higher rate features at lower rate levels, right? For more information, please come along to our poster. In terms of evaluation, clearly that we see that from subjective listening tests that a hierarchically structured clockwork model does indeed give us better prosody. We've got plenty of other results in the paper. Please come along to the poster if you want to hear some samples as well. Okay, that's poster number 110. Thank you very much for listening.